Hello my dear friends, I am Shubham from LearnoHub, the free learning platform where you can study physics, chemistry, maths, biology absolutely for free at learnohub.com. So then, let's start. So friends, as you all know, we are studying your ICSE Chemistry class 10th chapter number 5, and so far we have completed 4 chapters. So now in this video we are going to study the first two topics of this chapter, that is Gay-Lussac's law of combining volumes, and second one is the relationship between vapor density and molecular weight of a gas. Okay, so I am following your 2023 syllabus for your ICSE exams, and throughout that syllabus, okay, we are having 4 topics majorly to study. Out of that, we are going to cover 2 topics in this video and the rest topics in the next video. Okay, along with the topics which we are going to cover, we are also going to solve numericals at the same time, okay, so that you would be able to understand the concept in a good manner, in a very well manner, and then you could also know how to apply those concepts to solve the numericals. And mostly I would include the questions which have been asked in your ICSE examinations. Okay, so without wasting much time, let's start and let's rock. Okay, so before starting to learn this chapter, the first question, yes, right, you're right, we should know first that why we should study this chapter. Okay, so apart from your that answers, the normal answers that it is in our syllabus, if we won't study and all those things, blah blah blah. Okay, but let's see why to study mole concept and stoichiometry. So first of all, this mole concept topic is completely deleted from your syllabus. Okay, though the chapter's name is mole concept and stoichiometry, but we are not going to study it. Okay, so bad, right? But don't worry, in your higher grades you are definitely going to study this mole concept, okay, for sure. Now let's move on to the stoichiometry term. So yes, we are going to study the some part of stoichiometry in this chapter. Okay, but before starting to study this, yes, we should know why we should study this, and for that let's first understand what actually stoichiometry is, okay, in very crisp way. So this is derived from 2 Greek words. One is stoichion, okay, and next one is metron. Okay, so the stoichion simply means element in Greek, and metron means measure. Okay, so now we could figure out that this stoichiometry means it has something with the elements and the measurement. Okay, so what actually we are doing in stoichiometry is we are just dealing with the calculation of masses or volumes of the reactants and the products involved in a chemical reaction. Okay, now in this chapter we are not going to calculate the masses of reactants and the products in the chemical reaction. What we are going to do is we are going to calculate volumes of the reactants and the products in a chemical reaction. And which reactants and products here we are talking about? We are talking about the gaseous reactants and the products. Okay, now how we are going to do this? Very simple. We are going to do this with the help of this first topic of this chapter, which is Gay-Lussac's law of combining volumes. This law will help us to calculate the volumes of reactants and products which are gaseous in a chemical reaction. So suppose, to make you understand the importance, suppose I am having a X gas, okay, I am mixing this with the Y gas, or I am asking them, both of them, to react, okay, and I am getting a Z gas. Now suppose I know that how much Z gas is getting formed, okay, but I don't know how much X and Y gases are reacting. So this problem we can deal with if we study this law. Okay, so it's interesting, right? Just by knowing the volume of our product, we can find out the volumes of the reactants, right? Very interesting. Next is, we are going to study the relationship between vapor density and the molecular weight of a gas. Okay, no need to go in details of this concept right now. And next topic we are going to study is percentage composition and empirical formula. Okay, now why I'm not talking about this molecular formula because right now this topic, relation between vapor density and molecular weight of a gas, percentage composition and empirical formula, all these topics are going to help us to find out the molecular formula. Okay, so if we could understand the importance of finding a molecular formula, then it's like obvious that we should study all these three topics, the remaining three topics, right? Now, why is it important to know the molecular formula? You would say, sir, why is it so? See, suppose I have given you a compound, okay? But now you don't know what actually that compound is. So, you know it's a chemical compound and you would not dare even to touch that compound, right? Because it may be dangerous. So, now if I would tell you the molecular formula of the compound, suppose I am telling you the molecular formula of this compound is NaCl. Just the moment you know that, oh, the molecular formula is NaCl, which means this compound is sodium chloride, the next moment you would make a lime water of it, right? And you would drink it. So this is the difference between knowing the molecular formula of a compound and not knowing the molecular formula of a compound, right? When you are knowing the molecular formula of the compound, you are actually knowing what compound it is. But if you don't know the molecular formula, you don't know what compound it is. Then you cannot use it, you cannot do anything with it, okay? You would be just afraid of just touching it also. So this is the importance of finding the molecular formula. Now I hope you are convinced with studying all these topics, right? So then let's start. Okay, so now let's see Gay-Lussac's law of combining volumes. Okay, now before understanding what actually Gay-Lussac stated in his law, first let's try to understand what actually he observed. Okay, and based on his observation, he gave that law. So understanding the observation is very important because once you know what he observed, you can easily state his law. Okay, you can easily write his law. Okay, so what he did is in 1800s, like in 1808 sometime, so he observed this reaction, the reaction of hydrogen with oxygen to form water vapor. Okay, so this is not the liquid water, this is water vapor. Now I would balance it first. So yes, so what he observed is when 2 liters of hydrogen gas is reacting, okay, with 1 liter of oxygen gas, 2 liters of water is produced, okay, and he observed this at same temperature and pressure. Okay, it just means that he just measured these volumes, okay, at same temperature and pressure. So let me generalize this thing. So liter is a unit of volume, right? So I would just replace this liter with volume word. Okay, so what he observed is 2 volumes of hydrogen gases is reacting with 1 volume of oxygen gas to produce 2 volumes of water, and this never changed. Okay, and this never changed, these volumes never changed when he was measuring these volumes at same temperature and pressure. Okay, always he found that 2 volumes of hydrogen would react with 1 volume of oxygen only and it would form 2 volumes of water. Now he was fascinated with this thing. So what he did is he just tried to write the ratios of the volumes of this gaseous reactants. So here there are 2 gaseous reactants, hydrogen and oxygen. Now if we would write the ratios of the volumes of these 2 reactants, okay, so what is the volume of hydrogen here? 2. What is the volume of oxygen here? 1. So the ratio is 2:1. Okay, so this ratio he got, and this was a simple whole number ratio, right? See, you can see here, these are 2 whole numbers, 2 and 1, and this ratio is a simple whole number ratio. Now what he did is, again, see, he tried to find out the ratio of the volumes of a gaseous reactant with a gaseous product. So suppose I am taking this hydrogen and water. Now this is the ratio of volumes of hydrogen is to water. Now what is this ratio? See, 2:2. 2 volumes of hydrogen, 2 volumes of water. Now what would be this ratio? 1:1 it would become, right? So this is also a simple whole number ratio. Again, he just tried to find out again he just had a look over the ratio of oxygen is to water, the another gaseous reactant and the gaseous product. So what was the ratio of volumes of these two? See here, 1 volume of oxygen is to 2 volumes of water. Again 1 is to 2. So again a simple whole number ratio. Now he thought that let me check this with the other gaseous reactions. Okay, so he studied the other gaseous reactions, and then again he found the same observation. Okay, he again found that the gaseous reactants were having the volumes in the ratio, and this ratio was a simple whole number ratio. Same way, the gaseous reactants and the gaseous products, okay, their volumes were again the same simple whole number ratios. Okay, not the same, but the simple whole number ratios. He again found the same thing. So what he generalized and gave this law, Gay-Lussac's law of combining volumes, because he found that gases are reacting in volumes. See here, you can see 2 liters of hydrogen is reacting with 1 liter of oxygen. Okay, so what he stated is when gases react, here you can see hydrogen and oxygen are reacting. So they do so in volumes, just now we have seen, okay, which bear a simple whole number ratio. Okay, see, they are bearing a simple whole number ratio to each other. Just like in the case of hydrogen and oxygen, which was forming water vapor, we have seen, see this gaseous reactants, okay, these gases are reacting in volumes, 2 volume and 1 volume, and they are bearing a simple whole number ratio, okay, with each other first, and then with the gaseous products, okay, as well as to the volumes of the gaseous products. Hydrogen is having a simple whole number ratio with the volume of water. The volume of hydrogen is having simple whole number ratio with the volume of water. Same, the volume of oxygen, okay, is having a simple whole number ratio with the volumes of water. In the same way, he just stated the same thing. And the condition also, the last thing is the condition, provided that all the volumes are measured at same temperature and pressure. Okay, very simple. So the only here important thing which you have to remember is this Gay-Lussac's law of combining volume is applicable to gases only. Okay, the reactants and the products in a chemical reaction, if they are gases, then only this law is going to be applicable for them. Okay, now out of all these things, what you have to simply remember is, or what this law is simply telling us, and what we have to actually apply while solving the problem is this simple thing. Okay, that is, gases are reacting in specific volumes, right, with each other. Just now we have seen the hydrogen gas is reacting with oxygen gas, but 2 volumes of hydrogen gas is reacting with 1 volume of oxygen gas, and then it is producing 2 volumes of water. Okay, it would never happen that 1 volume of hydrogen would react with 1 volume of oxygen and it would give 2 volumes of water. It would never happen. Okay, so what he concluded, or what we should conclude from his law, simply is gases are reacting in specific volumes. Okay, and these specific volumes won't change at all to produce gaseous products having specific volumes. Okay, here as you can see, hydrogen is 2 liters of hydrogen is reacting with 1 liter of oxygen, and then it is producing 2 liters of water. Okay, not a change in the volume would be observed. Single change, there would be no change in the volume which you would observe here. Okay, always 2 liters of hydrogen would prefer to react with 1 liter of oxygen only, and it would form 2 liters of water. Very clear? So this thing you have to remember just for solving the problems, and your work is done. Okay, so now let's see some numericals. So first is calculate the amount of each reactant required. Okay, so these are the 2 reactants. We have to calculate their amounts In volumes, absolutely. We are here talking about, I have told you in the first slide itself that we are just going to find out the volumes of the gaseous reactants and the gaseous products in this chapter. So here we are talking about the volumes of this each reactant which is required. Okay, in this question they are asking us the volumes of each reactant required to produce 750 ml of carbon dioxide. Okay, so here the carbon dioxide getting produced is 750 ml. What else they have given us? They are saying that 2 volumes of carbon monoxide, okay, this is carbon monoxide, so I am writing here 2 volumes of carbon monoxide combines with 1 volume of oxygen, okay, fine, 1 volume of oxygen to produce 2 volumes of carbon dioxide. Okay, very well. So these all things are given to us. Now you also know what we are going to find out. Now how we are going to do this? See, first of all, they have already given in the question itself that how many volumes of the gaseous reactants are reacting and producing how many volumes of gaseous products. But if they haven't given you this information, okay, suppose this statement is not given, then how you would deduce this? So I will tell you a simple trick. See, you just have to pay attention to this reaction which is given to you, okay, this one. Okay, first you have to check whether this reaction is completely balanced or not. If it is balanced, well and good. If it is not balanced, then you have to balance it first. Why? Because see, after balancing, the number of molecules, okay, of the particular reactant or the product is same as the number of volumes of that particular reactant or product. See, here are 2 molecules of carbon monoxide. So I am writing 2 volumes of carbon monoxide is reacting with, see, 1 molecule of oxygen is there. So I am telling that 1 volume of oxygen, it is reacting with 1 volume of oxygen. And since here 2 molecules of carbon dioxide are there, so I am writing here it is giving us 2 volumes of carbon dioxide. Now just check it once with the given information. Is it exactly the same? See, yes. So in this way, now let's focus on finding the answer here first. So now I have told you how to just get this volumes as well. Okay, so suppose if they have not given your exams or in any question, you can just deduce it. So it's very important. Now how to get this volumes? First of all, we know that from the Gay-Lussac's law, a very simple thing, the last thing which we studied here, that gases react in the specific volumes, and what do they do after reacting in specific volume? They give us the gaseous products having specific volumes. So here also the same thing is happening. See, carbon monoxide, 2 volumes of carbon monoxide is reacting with 1 volume of oxygen and giving us 2 volumes of carbon dioxide. Very clear. This is not going to change. Is always these 2 volumes of carbon monoxide are going to react with 1 volume of oxygen and 2 volumes of carbon dioxide we are going to get. And how can we say this very firmly? By Gay-Lussac's law. So yes, we are going to apply that law only. So I would start writing the answer. See, by Gay-Lussac's law, okay, what we know is, see here, 2 volumes of carbon monoxide is reacting with 1 volume of oxygen and producing 2 volumes of carbon dioxide. So can I say that 2 volumes of carbon monoxide are required to produce 2 volumes of carbon dioxide, right? Very, very logical. So I am writing it here. 2 volumes of carbon monoxide is required to produce 2 volumes of carbon dioxide. Okay. How I am getting this? By Gay-Lussac's law. Again, I can say that, see, 1 volume of oxygen is required to produce 2 volumes of carbon dioxide, right? So I am again writing here. 1 volume of oxygen is required to produce 2 volumes of carbon dioxide. Now why I am writing this? Because we have to find out the volumes of carbon monoxide and oxygen, right? When 750 ml of carbon dioxide is getting produced. So we are going to use each one of the information from this Gay-Lussac's law, whatever we are getting, to find out the volume of each reactant. So what I can say that simply, see, now I am trying to find out first the volume of carbon monoxide, okay, required to produce 750 ml of carbon dioxide. So from Gay-Lussac's law, I can say that 2 volumes of carbon monoxide are required to produce 2 volumes of carbon dioxide, right? But here I have to find the answer in ml, right, milliliters, because they have given me the volume of carbon dioxide in milliliters. So I can simply write, instead of that volume term, I can replace that volume term with ml here. Okay, so I can write 2 ml of carbon monoxide is required to produce, again, 2 ml of carbon dioxide. Okay. Now, this thing we know by Gay-Lussac's law, right? So it's now very simple. Now, how many mLs of carbon monoxide? Okay, so I'm taking this how many as x. So x mLs of carbon monoxide, okay, would be required to produce 750 ml of carbon dioxide, right? Very simple. Now you know how to solve these things. We know that 2 ml of carbon monoxide is required to produce 2 ml of carbon dioxide. So to produce 750 ml of carbon dioxide, the same thing, see, 2 ml is 2 ml for producing 2 ml, we are requiring 2 ml. So for 750 ml, for producing 750 ml, same, we would require 750 ml. Okay, so I know you are smarter. You can directly deduce this way the answer, or else you can use the same chocolate problem method. So we know that, see, 2 ml of carbon monoxide is required. Okay, I'm writing it. 2 ml of carbon monoxide is required to produce 2 ml of carbon dioxide. Then x ml of carbon dioxide is required to produce 750 ml of carbon dioxide. X ml of carbon monoxide is required to produce 750 ml of carbon dioxide. Okay, the terms in the numerator are of carbon monoxides, the terms in the denominator are of carbon dioxides. Okay, now we know, I would cancel out this all mLs because I'm going to find out the value of x simply. 2 is also cancelled, so x would be is equals to 750. See, so 750 ml of carbon monoxide would be required to produce 750 ml of carbon dioxide. Very simple, we got our first answer. Now in the same way, we have to find how much ml of oxygen would be required to produce 750 ml of carbon dioxide. Okay, so you can pause it here and then you can follow the same method and try to find out on your own. It's very simple. Okay, so I hope you would have tried. So now I would tell you how to find the answer. If you have tried, you can check the answer. If you are not able to find out the answer, let's see. So same way, by Gay-Lussac's law, now we know that 1 volume of oxygen is required to produce 2 volumes of carbon dioxide, right? So I'm just replacing that volume with ml. So 1 ml of oxygen is required to produce 2 ml of carbon dioxide. Okay, now x ml of oxygen. Now we know this thing by Gay-Lussac's law. So we can say that then x ml of oxygen would be required to produce 750 ml of carbon dioxide, right? Now we have to just find out the value of x and our job is done. So see here, 1 ml is giving us 2 ml. So then how much ml would give us 750 ml? So if you are smart enough, you would directly tell that this x would be half of 750, right? It would be around 375 ml. Okay, or else if you want to find out the answer, you can again use that chocolate problem method and you can find out the answer. Same, 1 ml of oxygen is required to produce 2 ml of carbon dioxide. So same, x ml of oxygen would be required to produce 750 ml of carbon dioxide. I'm cancelling this ml throughout. Then what is happening? I'm finding the value of x. X is equals to 750 by 2. It's the half of 750, so it's 375. Okay, see the same thing, 375. So 375 ml of oxygen would be required to produce 750 ml of carbon dioxide. Finally, you can write this statement. Okay, and in the same question, okay, the second sub question is state the law associated in the question number 1 above. Okay, so we know which law we have used, Gay-Lussac's law, and they are asking us just to state the law. So we have to write the statement of the Gay-Lussac's law, okay, which we have already seen. Okay, so you have to just write the entire same statement, but you have to take care of the keywords as well while writing, and you won't miss the keywords if you have understood the Gay-Lussac's law very well. Okay, so moving to the next question. The previous one was asked in your exams in 2020. Okay, now this was asked in your exams in 2018. So I have deliberately picked up the questions which have been asked in your exams because you would get an idea that which type of questions are being asked, okay, based on this concept. So second one is ethane burns in oxygen, and I have taken care that the different types of question I would be solving here, not the same type, because now once we know one type of question, you can easily solve on your own. Okay, so now let's see the next one. Ethane burns in oxygen to form carbon dioxide and water. You can see here, this is ethane. Okay, don't worry about it because we are going to study organic chemistry, the last chapter, in detail. But till that point, you just see that, you just understand that this is ethane. Okay, C2H6 is ethane, and it is burning in oxygen to form carbon dioxide and water. Okay, according to the equation. Now what they are telling us is 1250 cc. Okay, here cc means cubic centimeter. Okay, or we can simply call it cm cube, and this cm cube simply means ml. Okay, so what they are telling us, 1250 ml of oxygen. Okay, just they have changed the unit of volume. They are using the unit of volume as cm cube, which is same as ml. We can call ml as cm cube as well. Okay, so if 1250 cm cube of oxygen is burnt with 300 cm cube of ethane, what they are asking us is to calculate the volume of carbon dioxide formed. Okay, this volume of carbon dioxide formed and the volume of unused oxygen. Okay, unused. Now this is something different. See, first of all, like previous question, they haven't given us how much volumes are reacting with, how much volumes and how much volume of product is formed, right? So we have to first figure this thing out. So it's very simple. We have to just check whether this given reaction is balanced or not, first of all. So yes, this is balanced reaction. Okay, you can pause the video here and you can check on your own self, check on your own. Just to save the time, I'm telling you, I have checked it, it is balanced. Now the next point is, when it is balanced, it's very simple, because the number of molecules is same as the number of volumes. So here it is telling us that 2 volumes of ethane are reacting with 7 volumes of oxygen, and they are forming 4 volumes of carbon dioxide and 6 volumes of, not 6 volumes, sorry, we should not deal with this water itself, first of all, because it is not asking our question itself. Okay, no need to go into this water part. Okay, so here we go. First thing we have figured out, and now we can apply the Gay-Lussac law, because we know, yes, 2 volumes of ethane, only 2 volumes of ethane will react with 7 volumes, not more than 2, not less than 2. 2 volumes will only react with 7 volume of oxygen, and it will form 4 volumes of carbon dioxide, not more than 4, not less than 4. Okay, same way, not more than 7, not less than 7, exactly the same volume, the specific volumes we have found out. Now let's apply the Gay-Lussac law first to find out the volume of carbon dioxide, okay, which is formed. So what we can do is, here in this question, the trick is not to use the volume of oxygen to find out the volume of carbon dioxide. You have to use the volume of ethane to find out the volume of carbon dioxide. Okay, now why is it so? Why I'm telling you not to use the volume of oxygen? Because see, they are asking in the question itself volume of unused oxygen. So this means that out of this 1250 cubic centimeter of oxygen, not all oxygen is getting burnt. Okay, so we cannot use this volume. Okay, because see, not because this 1250 ml of oxygen is not getting used. Okay, there is some oxygen which is left unused. So we are not using the volume of oxygen, okay, to find the volume of carbon dioxide. In case, in other words, we are using the volume of ethane to find the volume of carbon dioxide. Okay, because from this question we are understanding that complete burning of ethane is taking place. Okay, because they are asking us the unused oxygen. So this means ethane is getting completely used, but oxygen is not getting completely used. So let's use the volume of ethane to find out the volume of carbon dioxide. Simple. So the same thing we are going to apply Gay-Lussac's law. So by Gay-Lussac's law, okay, what we know is, now you know how to write the sentences. 2 volumes of, or else I would not write the volume itself, I would write just in the unit. In which unit they have given us? cc, right, cubic centimeter. So 2 cc, okay, of ethane is required. You can write in the entire sentences, you have to write in the entire sentences as your answer in exams. So is required to produce 4 cc of cubic centimeters of carbon dioxide. Okay, then we know that here 300 cc of ethane is getting used, right? So 300 cc of ethane, okay, is then required to produce. Now we don't know the volume of carbon dioxide which is formed. That's actually that's the actually thing we are going to find out. So I'm writing x cc of carbon dioxide. Okay. So 2 cc of ethane is required to produce 4 cc of carbon dioxide, or else I can write 2 cc of ethane is giving 4 cc of carbon dioxide. So 300 cc of ethane will give x cc of carbon dioxide. Okay. Now let's find the value of x simply. So 2 by 4 I can write here. Okay. 2 by 4 is equals to 300 by x. Now 1s are 2s are, right? And here x is equals to 300 into 2, which is 600 cc, right? So this means 300 cc of ethane, cubic centimeter of ethane, will give us 600 cubic centimeter of carbon dioxide. Okay, so we have found the answer of this first question. Okay, now let's move on to find the volume of unused oxygen. See, you can what they have given us is total oxygen which is taken is 1250. Now we have to find out how much oxygen is used. Okay, once we know how much oxygen is used, we would just subtract this with the total oxygen which is taken up for the reaction, and then we would get what is the unused oxygen. Okay, what is the volume of unused oxygen. Now what we have to do is we have to find out the volume of oxygen which is used, okay, for burning this 300 cc of ethane. Okay, so from Gay-Lussac's law we know that 7 volumes of oxygen are required to burn, okay, 2 volumes of ethane, right? See here. So I can just write here 7 volumes of oxygen, okay, is required to burn 2 volumes of ethane. Okay. Now here what I would do is I would just replace this 7 volumes with cc itself, okay, because we have to find the answer in cc. Okay, so 7 cc of oxygen is required to burn, okay, 2 cc's of ethane. Very clear? 7 cc of oxygen is required to burn 2 cc's of ethane. Okay, now then we can simply write x cc of oxygen would be required, okay, then x cc of oxygen would be required to burn, okay, 300 cc of ethane. Now we don't know how much cc of oxygen is required to burn this 300 cc of ethane, right? So I have just written x cc of oxygen would be required to burn 300 cc of ethane. Okay, now again we have to find out just the value of this x and we are done with our job. Okay, so how we can find out? Either by just writing 7 by 2, okay, 7 by 2 upon x by 300. Okay, so what it would give us? X is equals to 300 into 7, okay, 2100 upon 2, then half of 2100, 1050, right? So value of x would be 1050. So 1050 cc of oxygen would be required to burn 300 cc of ethane. Now we found out that out of 1250, okay, 1050 cc of oxygen is required to burn 300 cc of ethane. Okay, now we can easily find out what is the left unused oxygen then, because we know that this cc of oxygen is getting used. We already have this much. Okay, so we already have 1250 cc's, out of which this 1050 cc's are getting used. Okay, so the remaining would be Very simple. Okay, 1250 minus 1050, it is 200 cc. So this 200 cc of oxygen is the unused oxygen. Okay, the volume of unused oxygen. Okay, so we got the answer of this also. So you have to simply write in the words that volume of unused oxygen is equals to 1250 minus 1050 cc, which is equals to 200 cc. Now, one more important thing about these two questions which we have solved so far. So see, in this question, when you would study organic chemistry, you would know that the first four members are gases. So ethane is the second member, okay, of the alkane family. Don't worry about this stuff. You just try to understand that ethane is a gas. Very simple, okay, right now. Oxygen, you know, it is a gas, and carbon dioxide is also a gas. Yes, and we are dealing with these three species only. Okay, we are not considering here water, okay, because no use of water is there for us to solve the questions. Okay, so leave about the water. Now rest three things on for which we are applying the concept of Gay-Lussac law. We have ensured that yes, these three species are gases. So before applying the Gay-Lussac's law of combining volumes on the species, you have to confirm once that yes, whether these species are gases or not, because that law is only valid for gases. I have told you, very important thing which you have to remember: gaseous reactants and gaseous products. Similarly, the previous case, in this question also, the carbon monoxide and the oxygen, we know these are gases. Carbon dioxide formed is also a gas. So we could apply on those three species the Gay-Lussac's law of combining volumes. Okay, now let's see the third numerical. So propane burns in air, fine, according to the following equation. Okay, this is the equation. Now what they are asking is what volume of propane is consumed on using 1000 cm cube of air. I have told you cm cube simply means ml. Okay, 1000 cm cube of air, considering only 20% of air contains oxygen. Okay, so this is a quite tricky one. Okay, a simple trick is there, and then it's very clear. So it was asked in your exams in 2017. So what they are telling us, see, first of all, the propane, you should also know that propane is also a gas. Okay, yes, propane is gas, oxygen is gas, carbon dioxide is gas here, and we are dealing with these three only for now, and we are going to apply the Gay-Lussac's law on this. Okay, so first of all, this thing is clear to us. Next thing, what they are telling us, propane is burning in air. Okay, here, so suppose this is the air which we are talking about in this question. Now what else is given to us? What they are telling us, that we have to find out volume of propane. Okay, this volume of this propane consumed on using 100 ml of air. So this air's volume they have given us, it is 1000. Okay, it's 1000 ml of air. Okay, this is the volume of air. But what they have said us is, considering only 20% of the air contains oxygen, out of this 100% air, only 20% of air is containing oxygen. Okay, so this means that out of this 1000 ml of air, not 1000 ml of oxygen is there. Okay, the 20% of 1000 ml is oxygen. Okay, 20% of air contains oxygen, which means 20% of this 1000 ml is oxygen. Now what is 20% of 1000 ml of air? Okay, we can simply solve this. You all know 20 by 100 into 1000. Okay, so we would get 20% of 1000 ml air, which is, see, 20 into 10, 200. So 200 cm cube or 200 ml of oxygen here we are talking about. Okay, this was the slight trick in this question. Okay, which would take you to the wrong answer, because you would consider 100 cm cube of oxygen here. Okay, for finding out the volume of propane. Now you know that how much oxygen is actually there. 200 cm cube of oxygen is there, which we are talking about. Okay, now what they are asking us is to just find the volume of this propane. Okay, now we know the volume of oxygen. This is 200 cm cube. If we know the volume of the gaseous, either reactant or a product, one of it, so we can easily find out the volume of rest gaseous reactant or product. Now here they are asking us the volume of gaseous reactant. So what we would do first, we would try to figure out the how much volumes of propane is reacting with how much volumes of oxygen to give how much volumes of carbon dioxide. Okay, now here no need to go into carbon dioxide as well. We would just figure out between these two because we are dealing with these two only. We need to just find out the volume of propane and we are going to find out with the help of oxygen. Okay, so see, from this reaction we can clearly make out one molecule of propane is there. Okay, this is a balanced reaction. You can check on your own. I have checked it. Okay, so one molecule of propane is required. This means one volume of propane, okay, is getting burned completely in 5 volumes of oxygen, or we can say in another manner, 5 volumes of oxygen is required to burn 1 volume of propane. So 200 cm cube of oxygen would be required to burn x cm cube of propane simply. So by Gay-Lussac's law, okay, we know that 5 volumes, I would just replace this 5 volumes with 5 cm cube. So 5 cm cube of oxygen, okay, which we have found from here. Okay, so 5 cm cube of oxygen is required to burn how much? 1 cm cube of propane. Okay, so therefore 200 cm cube of oxygen, okay, would burn x cm cube of propane, right? Now we have to just find out the value of this x and our job is done. Okay, so 5 upon 1 is equals to 200 upon x. Okay, direct proportion. So 5 1s are 5 4s are 0. Okay, so x is equals to 40. So x is equals to 40. This means that 200 cm cube of oxygen would burn 40 cm cube of propane. Okay, and this thing only they have asked what volume of propane is consumed. So 40 cm cube of propane is consumed on using 1000 cm cube of air, considering only 20% of air contains oxygen. Okay, the previous step, this step you can write it in the sentence form. Okay, that as in the question they have said us that 20% of air contains oxygen. So this means that the volume of oxygen, okay, which is actually reacting with our propane is equals to this, 20% of 1000 ml, and then you solve this and you would get 200, right here, 200. So the volume of cm cube, okay, so volume of oxygen which is actually reacting with the propane is 200 cm cube. So this is the first part and this is the second part. Okay, so now let's see the relation between vapor density and the molecular weight of a gas. Okay, so before that, let's first quickly revise what actually molecular weight is. Molecular weight is simply the weight of a molecule, right? Now, how we find the weight of a molecule? We know molecule is made up of atoms, right? And if we find the atom's weight, okay, all the atoms weight in a molecule, we get the molecule's weight, right? So what we have to do is just add the atoms weight, okay, all the atoms weight in a molecule which are present in a molecule, and then we get the molecular weight, and we call this atoms weight as atomic weight, right? We know this thing. We denote it with a unit called AMU, okay, atomic mass unit. These all things we have studied in our previous grade. So what is simply molecular weight? Molecular weight is the sum of the atomic weights of all the atoms in a molecule. Okay, and these atomic weights are expressed in the unit atomic mass unit. So our molecular weight would also have the same unit, right? Let's see with the help of an example. It would be very clear to you. Okay, so here's, before taking an example, I would advise you to just learn the atomic weights of these elements. Okay, it would be useful for you. Most of the time in the exams, whenever they ask you to find the molecular weight of any molecule, they give you the atomic weights of the elements. Okay, but sometimes it may not happen. for these common elements. Okay, for these common elements, they may not give you, so it's better to remember them. So it's very simple. See, hydrogen is the first element, so atomic weight is 1. Similarly, carbon 12. How you can remember this? See, atomic number of carbon is 6. Its double is its atomic weight. Same way for nitrogen, atomic number 7. Its double is its atomic weight. Then oxygen, atomic weight, atomic number 8, and its atomic weight is double, 16. Sodium's atomic number is 11 and its atomic weight is more than double, 23. Okay, so you remember in this way, sodium's is more than double. Again, sulfur, atomic number 16, its atomic weight is exactly the double, 32. Chlorine, atomic number 17, its atomic weight is again the more than double of its atomic number. Okay, so here see, sodium's case and chlorine's case, their atomic weights are more than the double of their atomic numbers. Okay, rest are exactly the double. Okay, and hydrogen is 1. So very clear to you. Now moving ahead, let's see an example. So suppose I'm asking you now to calculate the molecular weight of ammonia. Okay, quickly you can pause the video here and try on your own. Okay, so I hope you would have tried. So let's see. Now molecular weight of this molecule I would find by adding the atomic weights of all the atoms, right, present in this molecule. Now how many atoms are there in this molecule? There are 4 atoms. 1 is of nitrogen and there are 3 of hydrogen. Okay, so I should know the atomic weight of nitrogen here. So nitrogen's atomic weight is 14. Okay, so 14 just now we have studied. Then there are 3 hydrogen atoms. So one hydrogen atom's atomic weight is 1, right? So I can just simply write 1 plus 1 plus 1, or else I can just write 3 into 1, right? It's the same thing. When 14 plus 3 into 1 is 3, 14 plus 3 is 17, right? So atomic weight of ammonia is 17, but here don't miss the unit, atomic mass unit. Okay, very clear, understood? So now let's quickly solve a question which was asked based on this molecular weight concept in your exams, okay, in 2019. Now this question is a mixture of 2 concepts. Here they are asking us arrange the following according to the instructions given in the brackets. So this is the instruction given to us. What is the instruction? In the increasing order of the molecular weight. And what they are asking us to arrange? This 4 compounds: ethane, methane, ethene, ethyne. Now you would say, sir, what is this ethane, methane, ethene, ethyne? We don't know these things, right? Now you would know this when you would study organic chemistry, the last chapter. Okay, don't worry. For now, that's why I told you this question has a mixture of concepts from 2 different chapters. So the molecular weight concept is from this chapter. So we are trying to solve this question. So don't worry, I'm going to tell you the molecular formulas of all these 4 compounds. So then after that, you should find the molecular weights of all these compounds, and then we have to simply arrange them in the increasing order of the molecular weight. Okay, very simple it is, right? They have also given us hydrogens and carbons atomic weight. So I have told you, see, most of the times they give you, sometimes they may not give you, so we should be prepared, right, for the common elements. Now see, I would tell you ethane. Okay, ethane's molecular formula is C2H6. Okay, methane's is CH4, you must be knowing it, maybe. Okay, ethene's molecular formula is C2H4. Okay, and ethyne's molecular formula is C2H2. Okay, very clear. So now let's start finding out the molecular weights of all these molecules first. Okay, and then we would arrange it. So you can pause here, you can use these 2 atomic weights and find the molecular weight. Okay, so I hope you would have tried. Now let's see whether you have done it right or wrong. So see, C2H6 means there are 2 carbon atoms. Okay, so I can write 2 into 12, right? Instead of writing 12 plus 12, I can write 2 into 12 plus 6 into 1, right? Then 12 to the 24 plus 6, 30. So it's 30. Okay, next is methane. 12, again 12 plus 4 into 1, right? Hydrogen atoms atomic weight is 1. So there are 4 atoms. So I have just written 4 into 1. Okay, 12 plus 4 is 16. Moving ahead, 12 2s are 24. Okay, right? I'm now doing it quickly. And then 4 into 1 is 4. So 24 plus 4 is 28. And here 12 2s are 24. And 2 1s are 2. So 26. Okay. All these are in the terms of atomic mass units. Okay. Now what's left is we have to just arrange them in the increasing order of the molecular weight. So least is this 16. Okay. So first would be methane then in our answer, right? Then more than 16 is, see, 26. It is ethine. Then ethene and ethane. See, ethene 28, more than 26. And then ethene. And then more than 28 is 30. So ethane, right? That's it. We have arranged this in the increasing order of the molecular weight. Okay, so such type of questions are being asked. I am deliberately adding on these questions because you need to apply the concept from two different chapters. Okay. Okay, so now we have just quickly revised what is molecular, means quickly revised molecular weight, right? We have solved a question as well. Now it's time to see what is vapor density. Okay, and after that we are going to see the relationship between molecular weight and the vapor density of a gas. So what is vapor density of a gas? So vapor density of a gas is simply a ratio. Okay, so yes, I'm making a ratio. Now ratio between whom? Ratio between masses of, so mass of, now ratio between masses of equal volumes. Okay, so I'm taking here as volume V in both the cases. Okay, because here we are talking about equal volumes. So mass of volume V, volume V. Okay, now whose volumes we are talking about? Of gas and hydrogen in a ratio. Okay, so of gas, of hydrogen, right? And very important thing, under same conditions of temperature and pressure. This means that we are measuring this masses, okay, the mass of volume V of a gas and the mass of volume V of hydrogen at same temperature and pressure. Okay, both of these masses are being measured at same temperature and pressure. So this is simply the vapor density of a gas. Okay, when we have to find vapor density of any gas, what we would do is we would take volume, a particular volume of gas, okay, and we would measure its mass, okay, at a particular temperature and pressure. Then what we would do, we would take same volume of hydrogen, okay, and then we would measure its mass at that temperature and pressure at which we have measured the mass of this gas of volume V, okay, and then we would divide the masses and we would get the vapor density of this gas. Very simple, right? Now let's see the relationship between the vapor density of a gas and molecular weight of gas. So it's very, very simple. You have to just multiply 2 with vapor density of a gas and then magic, you would get molecular weight of that gas. Okay, very interesting. Now no need to study the derivation, okay, for this formula, how this formula came into existence. No need to study this because it is not in our syllabus. Okay, it is based on the Avogadro's law, and we haven't studied Avogadro's law because Avogadro's law is also deducted from our syllabus. Okay, so for now this is the relationship. You have to remember it because we are going to use it, as I have told you, when we are going to find out molecular formula. Okay, so be patient and wait till then because we are going to see that concepts in the next video. So friends, with this we have reached the end of this video and I hope you would have understood all the concepts we have learned so far. You would have enjoyed learning with me, but please do let me know this thing in the comment section. And जैसे कि आप सभी को पता है, LearnoHub मतलब free है पर best है. So stay tuned. We will see the remaining concepts of this chapter in the next video. Till then, bye bye and have a great day.